To też prawie ząbki są. Good evening. We start our second seminar this academic year. Our guest will be Suhani Gupta. He's a PhD student in Center for Theoretical Physics, Polish Academy of Science, working with Wojtek Helbing. And she did her master in Indian Institute of Science and Education and Research in Mohali. Floor is yours.
Thank you for introducing me. Good afternoon, everyone. My name is Suhani, and I'm a PhD student with Wojtek Helbing and Maciej Kwiatkowski at the Center for Theoretical Physics. Today, I would like to present the work that I have been doing with my supervisors as well as collaborators, which is broadly titled as Nonlinear Density Fields in Modified Gravity Cosmologies. To begin with, I would like to give a general layout of how structures form in the universe. So all the large-scale structures that we see today, from galaxies to halos, their existence can be traced back to very tiny perturbations in the early universe. These perturbations, by relentless action of gravity, they amplified over time to form anisotropies in the cosmic microwave background. And within these anisotropies, dark matter collapses to form halos, and it is within these halos that galaxies and clusters and all the visible universe forms. The early perturbations, they were small and can be studied, their evolution can be studied with linear approximations using the linear theory. And as time evolved, these perturbations, they grew within time and can no longer be studied using linear approximations. And we need to study them using, for instance, simulations. So you might have seen in the title that I mentioned modified gravity. So the standard ΛCDM model of a universe is based on Einstein's theory of general relativity. Since its inception, which was over 100 years ago, GR has been tested time and again on different scales and in different regimes, and it has passed all these tests with flying colors. But still, we consider modifying it. Why? So there are many reasons to it. I highlight those which are significant to us. So I mentioned that GR is tested very well in many regimes, but still there are many unexplored regimes where GR is not yet well tested, like intermediate length and time scales. So instead of extrapolating GR, general theory of relativity, to those regimes, we can consider a possibility of a more general theory of which GR could be a specific case. Also, within the standard ΛCDM model of the universe, the lambda, or the cosmological constant, is responsible for the cosmic acceleration, which has been shown in observations. But no known physical phenomena explains for this cosmic speedup. We invoke this lambda in GR, but lambda faces theoretical inconsistencies. And also within the framework of GR, we have dark matter, which is the dominant component of matter, and explains the stability of large-scale structures, and also dark energy, which is the general term for which is given to this kind of energy that explains for this cosmic speedup, of which lambda is a candidate. And despite years of dedicated research and experiments and observations to detect them, we are still completely oblivious to the nature of these components that dominate our cosmic configuration. These and many more factors, they persuade us to go beyond GR, and in our work, we study these modified gravity models, which are one of the way that we go beyond GR. In this, we consider additional forces, or what we call as a fifth force, which are due to some additional interactions between scalar field and matter, or by considering additional dimensions. And these, considering these additional interactions, we can explain for the cosmic speedup without invoking the lambda term. And also because they influence, which I will show later, they also influence the perturbation equations, and hence they have an influence on growth rate and structure formation and the associated measures and observables. So namely, in our work, we work with two modified gravity models. So one is FFR gravity, and the other is nDGP gravity. In FFR, we consider additional non-linear interactions between scalar field and matter, which are given by nonlinear functions of Ricci scalar, which hence the term FFR, where R is Ricci scalar. And in nDGP model, we consider that gravity, unlike other standard forces, also propagates to other dimensions. So because we have enhanced forces, this leads to enhanced structure formation. And here we can see, here I plot the growth of structures in these modified gravity models with respect to ΛCDM. Here, these are variants of FR. I will elaborate on them later. And these are variants of nDGP. And here we can clearly see that both the growth enhancement in both these models is dependent upon the time. And additionally, it is also scale dependent in FFR, whereas it is scale independent in nDGP. And in our work, we are working with cosmological and world simulations. So we have Elephant, a suite of modified gravity, dark matter only simulations. We have ΛCDM. We have two Husavitsky FFR form of gravity. This is the model parameter, where we have F6 and F5. F5 is a stronger variant than F6. And we have two nDGP variants, N5 and N1. Again, N1 is stronger variant than N5. And any modified gravity model that we are considering, it should satisfy GR constraints on regimes where it is well tested, like high density solar system. So most of the modified gravity models, they invoke something that is called as a screening mechanism, which, as the name suggests, screens the fifth force. So for instance, Husavitsky FFR implements chameleon screening, whereas nDGP implements Feinstein screening. So more details about these screening mechanisms can be found here, and if you want to discuss, we can discuss it later. And also, like modified gravity, because we want to explain the cosmic acceleration, it's a low redshift phenomena, so it makes sense to consider the data at low redshift. So we have data at redshifts between 0 and 1. So broadly, the talk is divided into two main parts. So in the first part, I will elaborate on building a semi-analytical framework to understand non-linear large-scale properties. And in the second part, I will try to explain how the nonlinear measures are also dependent on other factors within the modified gravity scenario. So let's focus on the first part first, building a semi-analytical framework. Why? I'll elaborate it. Okay, so whenever we study structure formation in the universe, the most basic quantity that we probe is the power spectrum or the correlation function. So power spectrum basically is the quantifies the number of modes in each wave in each wave number, and it's mathematically it's just a Fourier transform of the correlation function. And here I plot the power spectrum that we obtained from linear theory. We have a primordial power spectrum and we evolve it using a transfer function. And we have a simulation power spectrum, which is shown in the solid lines, which we directly count modes in simulation. So here we can see that at large scales, both simulation and linear theory predictions match. But as we move to smaller scales, we can see that the discrepancy between simulations and linear theory emerges, because gravitational instability leads to mode coupling and increases nonlinearities, thereby increasing the nonlinear power spectrum. But it is in this small scale regime where we expect constraints from our present as well as future surveys. So we really need to probe this regime where linear theory does no longer holds. And here we study, our best resort here right now is the simulation results. And I further plot the simulation power spectrum from ΛCDM and all the modified gravity variants that we have, which I highlighted previously, and we compare the power spectrum from these modified gravity models with ΛCDM. So we can clearly see that all models, all the variants, they are showing a different signal when we compare it. So thereby this makes a power spectrum a very sensitive probe to the modifications that we are making to the underlying theory of gravity. So as I highlighted that simulations are our best tool to probe the power spectrum, but simulations are not easily available. They are expensive, they are time consuming. And also if we want to consider modified gravity models, simulations become more expensive because unlike GR or ΛCDM, we do not understand them very well. We have a large parameter space. So thereby this makes it important that we have some tools that can give us reliable or quicker estimates to compute the power spectrum in these modified gravity models. So we work in this direction in which we want to build an analytical framework to compute the nonlinear matter power spectrum. We begin our work with using HALO model. So HALO model, it was proposed more than 20 years ago to explain to give statistical description of density fields where linear theory and perturbation theory fails, in a way to build a nonlinear matter power spectrum. So within the HALO model framework, the total power spectrum is given as sum of a one halo term and a two halo term. So one halo term considers the power within a halo, and two halo term considers the power between halos. So we can see here the one halo would dominate on small scales and two halo would dominate on larger scales. So here we plot the power spectrum, which we obtained from HALO model. So this blue line is the one halo term. We can see it dominates on small scales, and the red is the two halo term, which dominates on the large scales. And the total power spectrum from HALO model is basically this green line, which is the sum of the one halo and the two halo term. So to build this HALO model framework, we require to study some HALO properties. I have not written the explicit expressions of one halo and two halo terms here, but within them goes the formalism for HALO mass function, for HALO bias, and the concentration mass relation. So now let's understand these ingredients separately. So first is the HALO mass function. So HALO mass function basically tells us the abundance of halos in the universe. So mathematically, it's just like the number density of halos in a given mass interval. We can estimate it directly from simulations, and observationally also we can estimate it indirectly using studying clusters, and HALO mass function forms a very important tool in order to constrain cosmological parameters. The modern formalism of the HMF was given in the works of Press and Schechter, which is given here. So ρm is the matter density of the universe, m is the mass of halos, f sigma is the halo multiplicity function that actually encodes all the nonlinearities that are associated with halo collapse, and sigma is the amount of fluctuations. I will elaborate on this later. And here I plot the halo mass function for ΛCDM and all the modified gravity variants. And in the bottom, I compare the modified gravity results with ΛCDM. Again, we can see that in this mass range, because we have enhanced structure formation, so we expected that the number of halos will grow. which we can clearly see over here, and all models, they show a distinct departure from ΛCDM. Now elaborating on this sigma term. So halos, what are halos? Halos are basically fluctuations in the underlying density field. And to quantify these fluctuations, we study the variance of the density field, which is given by this expression. And when we plot this log sigma inverse, we take a inverse and then we plot its log with the mass of halo, we can clearly see a monotonic as well as a redshift dependent trend. So in a way, we can substitute for mass of halos the variance of the density field. And why is the substitution significant? We'll see here. So here we plot the halo mass function as versus the mass of halos for different redshifts. From redshift 0 to redshift 1, we see that halos, the number of halos increases as time elapses. So we can see that at redshift 0, we have more number of greater halo mass function than at redshift 1. But when we do a substitution from the mass of halos to the log sigma inverse term, we can clearly see that this explicit redshift dependence approximately eliminates. We can see that we can express halo mass function as a universal function across redshift. And this is important because it has been used a lot in literature to propose different fitting functions to compute this halo mass function quantity. Here, the SMT01 is basically one of the fitting functions that we used. This is for ΛCDM, and similar trend we also see for modified gravity models that we have. More interestingly, in our work, we found that the ratio of the modified gravity to the ΛCDM power, halo mass function, which I showed previously also, that is also universal across redshifts. So we can see all redshift trends, they tend to match. And we propose that we can give different fitting functions for this ratio, which is given here by this delta mg term. And we say that the modified gravity halo mass function can be computed by taking a product of this delta mg, which is the fitting function for this ratio, times any ΛCDM halo mass function we want. So this is advantageous again because we have very good high resolution simulations for ΛCDM. We have very good fitting functions that very accurately probe the halo mass function in ΛCDM when compared to modified gravity. So this delta mg term basically is a fitting function, which I mentioned, and it depends on what modified gravity variant we consider. For example, for FR, we have an exponential fitting function where A, B, and C are the parameters of the fit. They depend on what FR variant we are considering. So here, this black line is basically this fit. And in the bottom, we compare our results, which we obtained from using this equation, with the actual simulation halo mass function. And we can clearly see that we are very well within percent level accuracy when in the trusted mass regimes to compute the halo mass function. Similarly, for nDGP, we have a tan inverse fitting function. Again, here TQRS are the parameters of the fit. And again, we see that we are within percent level accuracy when we compute the halo mass function. Yeah. So the second ingredient for the halo model formalism is the halo bias. So what is halo bias? It basically tells us the relationship between halos and the underlying dark matter density field. So this relation is expected to be stochastic, nonlinear, scale dependent on small scales. But as we go to larger scales, this relation becomes independent of scale and depends linearly on halo mass. And that linear halo bias relation is what we need in the halo model buildup. So here we plot this relation for ΛCDM and all the modified gravity variants. And below we compare the modified gravity to ΛCDM halo bias. And contrary to halo mass function, where we see that structure formation enhances the halo mass function, here we see that bias tends to decrease. This is a result of the increase in dark matter cluster. And here we separately plot all the modified gravity variants and how the bias differs from ΛCDM. We see for the stronger variants, which are F5, N1, and nDGP1, the decrease is greater than what we see in the weaker variants. And moving to the third ingredient, which is the concentration mass relation, it basically tells us about how the density profile of a halo behaves. So mathematically, it is given as a ratio of the virial radius to the scale radius. The scale radius is basically a parameter within the fitting function. And again, we compare the modified gravity concentration mass relation with ΛCDM. So for FFR, we see that this relation is quite non-monotonic. And in nDGP, we see that this relation is quite monotonic with the different nDGP variant that we want to consider. So combining all these, we build the HALO model framework, and we then compare the result that we obtained from the HALO model power spectrum with the actual simulation results. And just to be clear, the HALO model was proposed for ΛCDM, but we see here that it performs very similarly in all the modified gravity models also. Namely, if you have this dotted line at the 5% accuracy regime, we see that it is within 5% accuracy up to 0.2, K 0.2, 0.3, and then 10% accuracy up to K 0.4, 0.5, which are still very large scales. And we also see the dip in the power spectrum, which we also is a known result for ΛCDM, and it propagates to our modified gravity variance. So the conclusion from this plot is that we are aiming to achieve sub-percent or percent level accuracy in cosmological parameter estimation. So in a way, we cannot use naive HALO model prediction, which are given here, in our cosmological parameter estimation. So we go beyond. What we do is we study this ratio, which is the modified gravity to the ΛCDM power spectrum. This ratio is important because it tells us about what modified gravity signature we can expect. So we plot this ratio for the linear theory, which is the dotted, for HALO model, which is the dashed, and for simulations, which is the solid. So we see this is for FFR, this is for nDGP. We see that at very large scales, all these ratios, they overlap. And as we move to smaller scales, the trends that are peculiar to each model, they emerge. For instance, in FFR, we see that there is a monotonic enhancement, whereas for nDGP, we see that there is a constant enhancement, even when it falls. The main takeaway from this plot is that linear theory does not match with simulation results on small scales, whereas the HALO model predictions, they qualitatively produce what simulations produce. Not quantitatively, but qualitatively. And using this, we propose that we can compute the power spectrum in nonlinear modified gravity models by taking a product of this epsilon term from HALO model with any nonlinear prescription for ΛCDM. Because we do this is advantageous again because for computing nonlinear ΛCDM power spectrum is we have many approaches that gives us very good, precise and accurate measurement for power spectrum in ΛCDM. And just multiplying with the HALO model formalism, we can obtain the nonlinear modified gravity power spectrum. So we plot this quantity here, and in the bottom we compare our results with actual simulation results. So earlier the 5% accuracy was between 0.2, 0.3. Now we can see that 5% accuracy even goes up to beyond K equal 1, even K equal to 2, which is very well within the nonlinear regimes where we have constraining power. This is for FFR, similarly for nDGP. And since the K range that we probe in our simulations, it is the range where we expect most of the signals from, for instance, lensing, the first natural application that comes in our work within the observation domain is to give analytical predictions for some weak lensing measurements. So here we give an analytical prediction for the convergence power spectrum, which is basically a statistical distribution of how matter is distributed on large scales. Within approximation, we can compute the convergence power spectrum by using this integral. Here is where this power spectrum from us is the input. We input the simulation power spectrum, the HALO model power spectrum, and the power spectrum we obtain from our framework. And again, we compare with simulations and find a very good accuracy for even nonlinear scales. This concludes the first part of the talk. So any questions?
So when you compare these to the simulations, is it possible? I mean, do you then compare it with the actual observations to prove if the simulations are correct or not?
Yeah, no, we do not do as of now with observations. We are right now we just compare with the simulations, the actual simulation results.
No.
Any other? Okay, so now let's move to the second part of the talk so this was building the analytical framework. Second part is to understand the nonlinear properties of large-scale structures and how the large-scale environment or other HALO properties can affect these large-scale properties within the modified gravity framework. So first we study the nonlinear measures and how the environment that's hosting those large-scale structure impacts this, and what modified gravity model, how modified gravity model influences this. So first we study the dependence of nonlinear measures associated with large-scale structures in the cosmic web environment. So the large-scale density field, it is not a random distribution. The large-scale density field, it manifests itself as a web-like structure, which we call as the cosmic web. So here is a picture of the large-scale density field. So here the dark points are the underdensities, or what we call as the voids. They are surrounded by walls, which are or the sheets. Then there is this filamentary network, which is called filaments, and then we have at the junction of these filaments, we have the nodes, which are high density. So when we go from voids to nodes, we go from lower densities to higher densities. And here the importance comes in, as I highlighted a bit earlier also, that the modified gravity models and the screening mechanisms they invoke have some density dependencies. So studying the modified gravity effects in the context of cosmic web, it actually can help us to break degeneracies that could be due to the effect of the environment or due to the modified gravity. So for instance, first we study the density distribution in the modified gravity models within the cosmic web. So here first, let's see the ΛCDM plot. We have the nodes, which are the highest densities, and then we have filaments, then we have the sheets, and then we have the voids. And the overall distribution peaks somewhere between sheets and voids. And very similar trend we also see in our modified gravity models. Okay, so here we cannot make any quantitative differences. To do that, we study the moments of density distribution. So first we probe is the variance, which is the width of the distribution. So here in the left plot is basically the variance computed for the entire density field for different smoothing radii. And we divide the environment, and we can clearly see that at very small scales, there is an environment dependence. This is just for ΛCDM, so no modified gravity right now. And we can clearly see that environment influences this moment. And all the results, they converge on large scales. And when we input our modified gravity models, here is the effect. So I show here only the stronger variance because the results, like for the weaker variance, the results are between the ΛCDM and the stronger variance. So here we have N1, nDGP, and here we have FR. So we can clearly see that for nDGP, the enhancement in variance is almost scale independent, whereas for FR, the enhancement is scale dependent. Also, we see that at small scales, there is also an environment dependence. Moving to the second moment of density distribution, which is the skewness, it tells us about the asymmetry in the distribution. Third moment. Thank you. Here we plot the ΛCDM skewness. Again, we are seeing an environmental dependence. And here we plot how skewness in modified gravity models varies with ΛCDM. So again, we see for nDGP, there's a constant enhancement, whereas for FR, we see that the skewness decreases. And again, we see that at small scales, there is a significant environment dependence. Similarly, the fourth moment, which is the kurtosis, we see that there is an interplay both of the cosmic web environment as well as the modified gravity in all the moments. Moving on from the density field, we studied halo properties also. So first, the halo mass function, which I showed earlier. Earlier was the halo mass function result for all the halos. Now we divide it into the cosmic web environment. So on the top is the plot with the division across the cosmic web environment. It's for the ΛCDM. And we can clearly see that low mass halos, they prefer to stay in filaments, whereas the high mass halos, they prefer to stay in nodes, which we can also see from the bottom plot. And when we input the effect of the modified gravity, again, we see that there is a different trend in different environments. So this black line I showed earlier also, it is for the entire density field, and all the colors, they correspond to different cosmic web environments. The second property which I show here is the halo spin. So halo spin is basically the sum of the angular momentum of all the particles that form a halo. And it is an important quantity to study how the halos would have assembled, because it tells us about the initial mass distribution where the region where halos form. So here, this is basically the sum of all the angular momentum of all the particles. And for practicality, we use this expression, which is given in this work. And again, we see that here, though mild, but there is some dependence of the spin on the cosmic environment. And more interestingly, we study how the modified gravity impacts this halo spin. So this is for FFR and this is for nDGP. Clearly, we see in FFR, the trend is both scale as well as environment dependent, and the enhancement goes even more than 15%. And for nDGP, we see that this enhancement is not very as strong, and also it's neither scale nor environment dependent. And moving to the third part, or like this second part of the second part, we study the dependence of the nonlinear measure now on other halo properties. So here we have the linear halo bias, which I highlighted earlier. It tells us about the relation between halos and the dark matter density field. And I said that on large scales, it can be expressed as a function of only halo mass. But many works later have shown that the large-scale clustering, which is given by this bias relation, it is also impacted by other halo properties, and also how halos assemble, which is given by the halo assemblies, which is called as the halo assembly bias, like how assembling of a halo or how formation of a halo is impacting its large-scale clustering. So this, for instance, is the trend for all halos. And if we invoke different halo properties to study this clustering, this trend changes. For instance, I use spin as well as halo concentration to study these properties. So for instance, for ΛCDM, we have all halos, the trend which I showed previously also. We have the lowest spinning and the highest spinning halos. So we can see that for both the subpopulations, the clustering is different. Even I do this for the concentration mass relation, which also I highlighted earlier. For the least and the most concentrated halo samples, the clustering is different than what we obtained for the all halo sample. And this is an important study because it goes into the study of galaxy clusterings, and it can impact systematic effects in building a halo and galaxy scaling relations. In our work, we want to actually see how modified gravity impacts this halo assembly bias signal. We know it impacts halo bias, but we want to see how it impacts the halo assembly bias. So for that, we check how much difference is there between the bias from the least concentrated or the most concentrated halos with all the halos, and also what is the difference between the bias from the most spinning halos and the least spinning halos from all halo bias, which we have plotted over here. So this is basically the difference between the bias of the most concentrated halos. This is the magenta, and the green is the least concentrated halos, and here the lowest spinning halos and the highest spinning halos. So this is for ΛCDM, which I showed earlier. We check this in our modified gravity models also, and here we can clearly see that there is no significant impact of the modified gravity model on the halo assembly bias signal. So now to conclude, so in my work, I will focus on modified gravity theories, which are the best theoretical alternatives we have to our standard GR scenario. And we are aiming to obtain percent or sub-percent level accuracy in parameter estimation. So to do that, we need to understand these all the different modified gravity models we have, and also ΛCDM to very good accuracy. So to do that, we need to know how these modified gravity models, they influence large-scale structures and all the measures and the observables that are associated with them. So in the second part of my talk, I highlighted that and how different environment and different assembly bias impacts this large-scale observations. And also I highlighted that the modified gravity models, the simulations are not very easy. They are time-consuming, and also they are not very cost-effective. So we need to build analytical frameworks that can give us reliable and quicker way to estimate parameters for these modified gravity models. So this was my talk. Thank you for your attention, and I will be happy to put some questions.
Question, please. Yes, please.
You showed a few statistical parameters such as theta and variance for your models. I see that if I understood correctly, for the small scales, those don't change much, but for large scales, that changes a lot.
I think it was like
The way around.
But my question is very simple. What does, I mean, besides the problem with the small, not really the problem, but the behavior for small scale and large scale results. What does, I mean, why did you use the variance and the skewness? I mean, what is that telling you in fact?
okay. So there are two main points. Thank you for your question. So first, when we plot this PDF, we want to see how there is this behavior in different cosmic environments and how modified gravity is affected. I do not see any visual difference, like from the first glance. So I wanted to see actually how quantitatively this is different. And also as structures evolve, the gravitational instability, it causes departure from Gaussianity. So more non-Gaussianity, more non-Gaussian distribution happens. So it becomes important that we study higher order moments within the density, within the density distribution. So yeah, these were the two main points I studied this. Yeah, sorry I didn't mention this. But yeah, thank you for this.
I should say these are the moments of the distribution. So
Yes.
people understand.
Okay, do we have more questions? There is, please.
Sorry, because theoretical theory is really not like structured at all. But so I was wondering, what would you need from like observational point of view, or like how to prove your theory of these the big force with observations? I maybe it's a tough question, but you know, I was just wondering.
Yeah, it's a tough question for me. So yeah, like as I highlighted, very vaguely, I highlighted that we can give predictions, for instance, for convergence power spectrum, where we take the input of power spectrum. So like I'm just telling you from my studies. Oh, okay. So we can actually also use many like for instance weak lensing measures, which so we can have like parametric equations for computing this weak lensing measure, where for instance terms like which show departure from GR, for instance like post-Newtonian frameworks. So where okay, so actually we can have parametric distribution, parametric form of equations that can actually tell us how the departure from gravity from GR. And these are then constrained by observations. Like
So if you would measure, so if you detect weak lensing, or I don't know if it also with strong lensing, but in general with gravitational lensing, then you can try to fit the lenses or the mass of the dark matter, or which whatever the lens, right? The lens, sorry.
yes, so like weak lensing is one of the most robust observational tool in which we can actually quantify departure from gravity, because in weak lensing we study the total matter distribution. So which is we study the total like baryonic as well as dark matter distribution, which is supposed to be impacted by whatever underlying gravity theory we have. So yeah.
Okay.
We do have more questions. Check if we have the question online. How we can see the no, I don't know how to do that. I'm too old. Okay, I don't see nothing. So let's thank our speaker again. Thank you very much. Thanks.